Hello, welcome to our 6th unit in AP Physics 1. This one's called Simple Harmonic Motion, and it's a great time to do this unit because there's not a ton of new material, but we are going to look at topics from our previous 5 units kind of all together right now in this new form of motion. Okay, we're going to be looking at things like kinematics, forces, even a little bit of circular motion, and definitely a little bit of momentum and definitely some energy in this unit. It's a really nice time to kind of review all of these things. So, to start off, sometimes you hear this called, instead of simple harmonic motion, simple harmonic oscillation. For some reason, the word oscillation really scares people. It's a very simple word. Oscillation simply just means some sort of repeated pattern. If you have a pattern that's repeating over time, you could say that that pattern is oscillating. And for us in particular, we're going to say that oscillation, at least in our context, what we're going to be looking at is repeated pattern in which we're really dealing with back and forth motion. Okay, that's any type of oscillation. There's many different modes of oscillation. The one that we're specifically looking at is simple harmonic oscillation. This has a couple of characteristics. This is a type of oscillation in which two main things happen. Number one, whatever object is oscillating is subject to a what's called restoring force. I'll talk about what that is in just a little bit. That is proportional to the object's displacement. And that restoring force is directed opposite the object's displacement. So those are the two characteristics of simple harmonic oscillation. Your object that is oscillating has a force put on it, a restoring force, that gets bigger as the object's displacement gets bigger. So the farther the object gets from the origin, or we might say from the equilibrium point, the bigger the force is, and that force is directed opposite the displacement. So for instance, if the object is displaced to the right, the restoring force acts to the left. And if you think about it, this should bring the object back towards the equilibrium spot. If the object is displaced to the left, the restoring force acts to the right. One of the interesting characteristics of this situation is if you graph position versus time for an object that is in simple harmonic oscillation, you get a shape that should be very familiar to you. You actually get a graph of the position versus time that looks like a sine curve. Or if you want to be fancy, you would call it a sinusoidal curve. Okay, so that's those are some of the characteristics of simple harmonic oscillation. We got to define a couple more things. So I said we'd talk about restoring force. Remember that when we talk about certain types of force, so for instance, let me say this. When we talked about net force wasn't a specific force that got put on an object. It was instead the sum of all the forces. Same for centripetal force. It wasn't a new force. It was some other object acting as a centripetal force. Restoring force is kind of similar. Other forces that you already know of act as the restoring force. The restoring force is just a description of what a particular force is doing. A force that tends to return a system to its equilibrium point. Okay? Whatever force tends to bring the object or the system back to equilibrium. We're going to be looking at two main cases of simple harmonic motion. We're going to be looking at pendulums and at springs. For pendulums, the restoring force is some component of the force of gravity. And we'll talk about exactly what that means and why it's a component of the force of gravity in a little bit. For springs, the restoring force is actually the spring force. Okay? Those are the forces that bring these systems back towards equilibrium. Before we get into our examples, we're going to do springs in this video. I want to very quickly define what we mean by period and frequency. Now, you might have had this defined in another class, but I see that students have trouble with these definitions and kind of mix them up, especially the frequency one. So let's try and get that out of the way right now. Definition of period is the amount of time for one complete oscillation or cycle to happen. One complete back and forth motion. The symbol for period is capital T, and the units are seconds. Okay, so the amount of time for one complete cycle to happen. So imagine releasing a pendulum. It swings from where it starts to the other side and then back. That's one full period. Okay, the amount of time that takes is a period. Frequency, on the other hand, is how many oscillations or cycles happen per second. So if the period is a length of time, the frequency is a count of how many times something happens. It's how many oscillations happen in 1 second. The symbol is lowercase f, and the units, if we're doing oscillations per second, that kind of implies that the units are 1/seconds, how many times per second. Or another way of saying that is Hz, which stands for hertz. Okay, hertz is the same as 1/seconds. They're units of frequency. There's a relationship between period and frequency, and it looks like this. Period is equal to 1 over the frequency, and since that's the case, we could reverse it and say frequency is equal to 1 over the period. So let me give you an example. Let's say you have a pendulum. It have to be a really small pendulum. Or let's say you have a spring system that completes 5 oscillations in 1 second. 5 per second, that would be the frequency. If we therefore want to find the period, we plug it into this equation. We do 1 divided by 5, we get 0.2. The period is 0.2, which makes sense because if something happens 5 times per second, that means it happens once every 0.2 seconds, once every 0.2 of a second. These two numbers are inverses of each other, 5 and 0.2. On the other hand, let's say you have a period of 0.01 seconds for something. That means it takes 0.01 seconds, 1/100th of a second, for some cycle to fully occur. What would the frequency be? Well, we take, since the period is 0.01 seconds, we plug in 0.01 down here for t, 1 divided by 0.01, and we get 100. And that makes sense. If something takes 1/100th of a second to happen, then it can happen 100 times per second, and that would be the frequency. The more experience you get with period and frequency, the easier this will get. What I want to get to now is a description of how springs, both vertical and horizontal springs, exhibit simple harmonic motion. We're not really going to get into the math with this. We're more going to get into just categorizing different quantities and variables and how they change as an object is in simple harmonic motion. Because like I said, there's not really a ton of new stuff here. There's like 2 new equations that are both pretty easy to use. The questions with simple harmonic motion really range more about talking about what certain variables are like at different points in simple harmonic motion. What is the kinetic energy like at this point? Can you make a graph of the restoring force at this point? That's what the questions ask. Before I start, I'm just going to say that what we're going to kind of do like a very usual step here. I don't know why I said unless or under. That should be unless. Okay, unless damping is mentioned, we assume that all energy in a spring system is conserved. ET equals ET. Damping is just a fancy word for friction. When you have these systems that oscillate, if something is damped, then that means that friction slowly takes some of that energy away and converts it to internal energy. So you can imagine if you have a pendulum that's swinging and it's undergoing damping, eventually it will come to rest because the kinetic and potential energy gets turned into internal energy. we're going to assume that unless it's mentioned, assume ET equals ET, which is just like we've done throughout most of the course. We ignore air resistance most of the time unless mentioned. We're now going to ignore damping. We're going to split our paper in two, or split this space in two, and we're going to start off with vertical springs. And again, remember, we're assuming ET equals ET. Here's how I'm going to draw this. Okay, it's going to take me a second to draw this and explain what this picture is. So here's a ceiling. Here's a box hanging from a spring. We're going to call that situation A. Here's situation B. We're going to say that situation B shows the box when it is at equilibrium, again, meaning the forces on it are balanced. And then here's C. And these are not three different springs. What I'm trying to show here is three different stages of motion. We're assuming that this mass, or box, or whatever, I'm going to call it a mass, on a spring has been, let's say, it's been brought up to this height with the spring kind of at its unstretched length, and it gets released. Down here is equilibrium, where the forces are balanced, and this is the lowest the spring system gets. So this is the highest point, equilibrium, lowest point. And what we're going to do is we're going to analyze the different variables that you might want to know about. So for position A, for instance, we might want to know something about the height. If you can think of that, you might say, okay, well, in addition to the height, maybe we want to know how fast it's moving, the velocity. Maybe we also want to know about the acceleration. So there's three kinematics variables. You might also want to know things like the kinetic energy of the mass or system. Since it's attached to a spring, you might want to know the elastic potential energy. Since it's moving up and down, you might want to know the gravitational potential energy at some point. And then finally, maybe you want to know something about the restoring force or the net force on, well, restoring force is a better word, the restoring force on our system. So we've got these different variables that are all changing. We're not going to actually assign numbers to a lot of these. We might assign zeros to them, but we're more going to focus on if something is at a maximum, if it's at a minimum, if something is going down, if something is going up, increasing or decreasing, or if something is just less than something else. That's what we're going to focus on. I think the easiest one to go with is the height. Very clearly, this is at the maximum height. So I'm just going to write max. At position Y, or at position A, the height is at a maximum. If you think about it, that also means that the gravitational potential energy must also be at a maximum. If A is the highest point that it reaches, which means it's not going up anymore yet, but it hasn't started to go back down, well, if it's not going up or down, that means that the vertical velocity must be zero. It's at its turning point. I hope you understand why that is. If something, it can't go up any farther, but it also hasn't started going down, it must not be moving. So that's at a zero. And if the velocity is zero, that also means the kinetic energy is at zero. Okay. So we set up here that the spring is unstretched, or at the very least, not stretched as much as it could be. So I'm just going to write down for US, I'm going to write down this is at a minimum. Okay? Because clearly, as this goes down, it's going to stretch out more and more, and US will increase. Maybe the trickiest one has to do with the acceleration and the force. Okay? We know that this velocity is zero, but that doesn't necessarily mean the acceleration is zero. As a matter of fact, if we're saying that this spring is not very stretched out right now, then what that means is that the force of gravity is always going to be on this mass. Okay, the force of gravity is always pulling this mass down. And in addition to that, if the force of gravity is pulling this down and there's not a lot of spring force or pulling upward because it's not very stretched out right now to counteract that, that's telling me that this is the biggest, that this is going to be the place where there's a really big net force or restoring force on this system because the force of gravity is on it and there's not much of a spring force to oppose it. Since the spring force, if this is not very stretched out right now, would be directed up and the force of gravity is directed down and the spring force is very small, I'd say that that means that the force, the restoring force, is going to be directed down because remember the restoring force always points back towards equilibrium. And since the spring force is about the smallest it can get right now, let's say it's at a maximum. Okay, so I guess what we're saying really here when we're talking about spring force part of the restoring force is actually also the force of gravity as well, because it's the force of gravity that's allowing this object to move back down or to accelerate back down. And remember from Newton's second law that since if the net force is negative and at a maximum, that means the acceleration must also be negative and at a maximum. And again, that's because of Newton's second law, F net equals ma. Okay, so there's the different variables that you might be concerned with for A. We could do the same thing at B. Now at B, I guess we didn't really, I prefer to make my system be so that at the lowest point, that's where the height is 0. This isn't at the lowest point yet, but we do know that the height is lower than it was at A. So we're going to say that the height is less than it was at A. That also means that the gravitational potential energy is less than it was at point A. All right. Since it's at equilibrium, that means the forces are balanced, which means there's no net force acting on the object. If there's no net force, there can't be any acceleration. So the restoring force at this point is 0 because it's at equilibrium. So is the acceleration. The spring has stretched out a little bit more, so the elastic potential energy has increased. So I guess I would say the elastic potential energy is greater than it was at A. And now we have to talk about the velocity and the kinetic energy. Since the acceleration is 0, that means that the object is not getting faster or slower at this point. Clearly, the object has started up here at 0, and it's gotten faster and faster since it got down to, or as it went down to equilibrium. If at equilibrium, it has no acceleration, and it was previously accelerating to that point, that means it's moving at its fastest when it's at equilibrium. So the velocity is actually at a maximum at equilibrium. And the kinetic energy is also at a maximum at equilibrium for the same reason. So see how these different variables change once we move down. We can do the same thing for C. And I know I'm writing a ton here. Hopefully you're catching up with me. And again, if you have any questions, always feel free to ask in class or electronically. At C, the lowest point in the motion, we know that the gravitational potential energy is 0 because the height is 0, so I'm going to mark zeros for both of those. This is the most that the spring is stretched out, so this is the elastic potential energy is at a maximum. Since it's at its lowest point, that means that it's not going any farther, but it hasn't started moving back up yet. The velocity is 0, and therefore so is the kinetic energy. Now, let's think about the forces acting now. This is at the lowest point. We know that it's going to oscillate back up. It's going to start moving back up towards equilibrium. That implies that the spring force upward is much bigger than the force of gravity downward. Okay? And that implies since this is the biggest the spring force gets, this is going to be the maximum upward net force. So now our restoring force is directed up, back towards equilibrium in the positive direction, and it's at a maximum. Which means our acceleration, due to Newton's second law, is also positive and at a maximum. Again, the AP test won't ask you to make this table, but they will ask you things like, where is the velocity at a maximum, A, B, C, or some other point? Draw a graph or pick out the graph that shows how the elastic potential energy changes as this object undergoes simple harmonic motion. So we're going to be working in class, we're going to be doing some examples of this, but you really need to focus for this particular unit on ways that we can represent this type of motion, okay? And to start that, I think it's really important to understand how these different quantities and variables change, okay? And we'll get lots of practice with that. Let's now talk about a horizontal spring. This is actually a little bit easier to analyze because you don't have something moving up and down, so you don't really care about gravitational potential energy. Again, we're going to assume that ET equals ET, and I'm going to draw it like this. So here's situation A. Situation B. And situation C. B is where the object is at equilibrium. This is the unstretched length of the spring, and notice that that's different from a vertical spring. Vertical spring, when it's at equilibrium, means the forces are balanced, which means it has to be a little bit stretched out. With a horizontal spring, that's not the case. This is where the spring is at its natural length. Okay, it has to be stretched out here because there's a force of gravity acting downward because of the mass attached to it. So you could imagine this, and again, these are 3 different states that we are oscillating between. You can imagine this as the spring and mass has been compressed to A, and then it gets released, passes through B as equilibrium. C is the farthest turning point that it gets to, and then it retreats back to B and back to A. By the way, that would be one full oscillation. That would be one full period. A to B to C, and then back to B, back to A. Or C, B, A, B, C. That would be one full oscillation. Same thing over here. You could even have something like B, A, B, C, B, or B, C, B, A, B. Those would also count as full oscillations. It's not just A to C. That's half an oscillation. Anyways, let's do the same thing where we list out our variables. So for A, some variables we might want to know about, maybe the position. If this is equilibrium, let's say this is where x equals 0, I would say that this is its negative maximum, or the maximum negative position that it might have. If this is the release point, then that means it's also a turning point once it's been oscillating for a little while. And we've seen that turning points mean that the velocity is 0. If something is turning around or about to change direction, it means it can't go any farther to the left, but also hasn't started moving to the right. In other words, it's not moving in the x direction. So the velocity is 0. The acceleration, if we think about the forces that are on the system, or on the block, or the mass, we have a normal force upwards, a force of gravity downwards. Those two balance, and they don't really contribute to the back and forth, side to side horizontal motion, so we can ignore those. But there is a spring force pushing, on A to the right. So since this is equilibrium, the spring force must be pushing in the positive direction. And since this is the most compressed the spring gets, it must be at a maximum. We can also talk about the kinetic energy. Since the velocity is 0, that's an easy one. The kinetic energy is also 0. We can talk about elastic potential energy. Since this is the most compressed that the spring gets, the elastic potential energy must be at a maximum. And finally, the restoring force, remember, is proportional to the acceleration due to Newton's second law. Since the acceleration is positive, directed to the right, and at a maximum, the restoring force, which in this case is just the spring force, is also positive and at a maximum. Okay? I know I'm going to run out of room here, but let's do the same thing for B. So we have X, V, A, K, U, S, and F. And we'll do the same thing for C. And yeah, I'll run out of room a little bit. X, V, A, K, U, S, and F. Now, for B at equilibrium, that's where we're saying x equals 0. So that's going to be a 0. For the velocity, if this is where the forces are balanced, that means that there is, if the forces are balanced, then that force is 0, which means no acceleration, which means the object is not speeding up or slowing down. We know that the object has been speeding up because of that push from the spring as it gets to equilibrium. So this must be the fastest that the object can go. The velocity, therefore, is at a maximum. The acceleration, because it's at equilibrium and the forces are balanced, there is no restoring force at this point, so I'll just label that as 0. The acceleration is also 0. Since the velocity is at a maximum, that means the kinetic energy is at a maximum. And the elastic potential energy, since the spring is not stretched, since it's at equilibrium, basically we've just taken away that force, the spring is at its unstretched length, the elastic potential energy is 0. So notice in these, one of the important things to notice is notice how the energy kind of transfers back and forth. At A, no kinetic energy, lots of elastic potential energy. At B, that's totally switched. Lots of kinetic energy, no elastic potential energy. And you can see the same thing in a slightly more complex manner over here with the vertical spring. But there we have to add in the fact that we're dealing with gravitational potential energy as well. Part C, just to finish up, we have, let's see, the object is at its positive maximum displacement. It's all the way to the right. It can't go any farther. So if it can't go any farther, it's not moving right, but it hasn't started moving back yet. Otherwise, it wouldn't be at its maximum displacement. So it's not moving at point C. The velocity is 0, which means the kinetic energy is 0. The spring force is the restoring force in this case. it acts back to the left, so it is at a negative, and this is the farthest the spring stretches in this direction, so it's at a maximum, which means the elastic potential energy is also at a maximum because it's the farthest the spring stretches. So notice we actually have two maxima here at A and C for elastic potential energy. And since the acceleration is proportional to the restoring force, to the net force, the acceleration is negative and maximum. And remember what negative means. It doesn't mean anything bad or weird about the acceleration. It simply means it's directed in the negative direction. We were kind of assuming that to the left is negative, to the right is positive, so this just means the acceleration is to the left, and it's really, really big. Again, hopefully you can see why we're kind of categorizing these variables here. I haven't explained any new physics to you at this point. I haven't explained anything new and that you haven't ever learned. We're just looking at it in a different sort of fashion because we haven't looked at this type of motion yet. One of the new things that we do have to learn, we want to know about the period of a system like this. We want to know about how long it takes to oscillate. Remember, that means one full back and forth motion. So how much time would it take this system to oscillate? What might that depend on? So some usual guesses, perhaps it depends on the mass of the object. Perhaps it depends on the spring constant. Remember, that's how stretchy the spring is. Symbol K. Perhaps it also depends on the initial displacement. Maybe if you push it back only a little bit compared to pushing it back all the way, that affects the period. I'm not going to tell you the answer. We're going to work this out in class, either with an actual experiment in the laboratory or with a simulation. But we are going to work this out in class, and we're going to actually come to an equation for this. We're going to discover what the equation is. That's a real quick introduction to simple harmonic motion. We still have to talk about pendulums, but that's going to be very, very similar to what we've discussed here. As always, if you have any questions, please feel free to get in contact with me, either in class or electronically. And next time we'll be back to talk about pendulums and actually finish up our notes on simple harmonic motion. Talk to you later.